To demonstrate how to use optical spectroscopy to study the molecular structure of material, let's consider a metal ion in a molecule. First, let's use this red dot represent the metal ion. And then we added the atoms surrounding this metal ion one by one. Okay, mode 1, 2, 3, 4. This is a 3D diagram. So all of these atoms, all of the 4 surrounding atoms are in the same plane as the metal ion. And then we added another 2 atoms along the vertical direction. Okay. And to see the exactly the shape, can we just connect this atom? So you can see here is a square plane. And if you connect other atoms, you can see a regular shape with 8 faces. It's called octahedron. By the way, octahedron is one of the Platonic solids. Although Platonic solids are hypothetical, this one is real. The red dot here is represent a metal ion, transition metal ion. In this case, is a copper 2. If you know how to use crystal field theory, then we can actually determine the energy levels for this particular transition metal ion, in which only d orbital for 1 electron can be considered. So this just draws the energy diagram for this structure. Actually, there are only 2 energy diagrams, although there are 5 d orbitals. This is called the degenerate case, and the more quantum states have the same energy value. Now, according to the resonance condition, we can argue that the energy level, energy difference between the 2 energy level will determine the transition, the absorption frequency of in the optical spectroscopy. So this is a resonance condition for the absorption, because on the right-hand side, it is this energy interval. On the left-hand side is energy of the photon with the frequency f. H is the Planck constant. Okay. So in this case, only one transition can be observed according to the theory. So the transition between the 2 can be observed. On the other, so that is, can we just give that experimental prediction here first? Only one peak can be observed in this case. Okay. Now, if I change the molecular structure slightly by shifting the 2 vertical atoms away, slightly away from the metal ion, what would happen? But first, we have to make sure that the 4 atoms in the plane are not changed. The position of these 4 in-plane atoms are fixed. Okay, so this is a vertical direction. So if I shift this atom, the top one, away from the metal ion, and so for the bottom atom, then we'll get something, get a distorted octahedron. So that's if you connect this atom, we'll see that distortion occur. This side become longer than before. That would be the distortion at molecular level. All right. So bear in mind that all of these atoms are electrically charged. So therefore, due to the distortion, very small distortion in this molecular structure, the energy level will change accordingly. Again, according to crystal field theory, and we can calculate, we can determine theoretically the energy level in the second case. Instead of 2 energy level, we will see 4 energy level, like this. Okay. Then, according to this resonance condition, this is called the resonance condition. So, absorption resonance. So it's a resonance condition. More transition can be determined. Let's consider the shortest wavelength transition. If we use a purple color to denote that the largest energy splitting, we can find this computer stop. Okay. We can use a purple color to represent the largest splitting. And then we use the blue color to represent that intermediate frequencies. And finally, we use origin color to represent the longest wavelength transition. And the last one, can we use green to represent the wavelength is slightly shorter. So in this case, theoretically, we can predict more peaks. The first one at with the highest frequency will be represented as a purple transition, followed by the 2 blue transition, and then we got the green transition and the 2 origin transition here. From these 2 spectra of absorption, it is apparent that a small change in the molecular structure, in this case, the distortion of the elongation of the octahedron, the spectral absorption will change dramatically. So based on this fact, we can actually work out the 3D molecular model for this copper-2 complex in any molecule. Could be in a small molecule like a drug, or in a macromolecule like a protein. Okay. So before I go, can we just draw the experimental setup for this optical spectroscopy experiment? So if I put the source here, so this it would be the source of light in the visible and the UV region, and that is incoming ray. This is a transmitted ray. In between, we will put the sample. We put a sample here, and then after that, we put a detector over here. So instead of using Newton's original experimental setup, here we just simply use a detector to measure the change in the intensity. So this is a sample. This is a light source. This is a detector. So the detector is used to measure the intensity as a function of wavelength. So this is actually the intensity of wavelength. This axis is wavelength. So this is a very good example. Actually, this example used in many textbooks to demonstrate how to apply optical spectroscopy together with theoretical modeling to obtain the actual structure of the metal ion complexes. On the one hand, the experimental result can serve as a guideline to build a model from scratch. On the other hand, the theoretical prediction can be theoretical prediction can be used to do more accurate experiment in order to obtain a realistic model for the metal ion complex. So that is why we say that spectroscopy plays a much more important role in studying molecular structure than microscopy.